So good morning all. So last class we have discussed about the effect of noise with respect to the SSB-SC system. Now with the help of that noise calculation model, we have identified the input SNR, we have identified the output SNR, then we have identified the figure of merit. Now what is the purpose of these SNRs? The purpose of SNRs is to identify the signal quality, whether the signal quality is good at the receiver end with including the effect of noise. If the effect of noise is more, your SNR will deteriorate. If the SNR value is less than 1, as I have discussed in the previous class also, if the SNR value is less than 1, that means effect of noise is more. And if the effect of noise is more, we cannot recover the original signal. So what we will do, we will modify our system through which the effect of noise can be suppressed, can be minimized, and we will strengthen the received signal so that signal power will increase with respect to the noise power. So if the signal power is increased with respect to noise power, which indicates the SNR value increases. If the SNR increases, our signal quality will definitely increase. So last class we have discussed about DSP-SC system as well as AM system also we have discussed. Now we will discuss with respect to SSB-SC system. Whatever the detection method we are using for a synchronous detection method. Then later on we will discuss the envelope detection. Okay, with the help of envelope detector also, how you can identify the signal to noise ratio at the input side, signal to noise ratio at the output of demodulator, and what is the figure of merit. Okay, so first we will discuss with respect to effect of noise in SSB-SC system. Okay. Now SSB-SC system means again we have to go through certain relations. With the help of that we will analyze what is the power available at the input signal, power available at the noise signal, and then we will identify what are the ratio at the input side, what is SNR, what is the output ratio at the demodulator output, and then we will take a ratio of the output SNR with respect to input SNRs, and we will see the figure of merit. Okay. So let me draw first the noise calculation model. So noise calculation model is first I will add noise to the received modulated signal. Here I will write it is received modulated signal. Okay, received modulated signal, that is S of T. Okay. Now at the receiver end, it must pass through the band pass filter because we need certain band. With the help of that band, we will extract our information. Either it is a lower segment, either it is a upper side. Then output of this band pass filter is SF of T and NF of T. That also we have discussed last class. Just we need to identify this relation according to the SSB-SC system. And then it enters to the demodulator. So in demodulator, what happens? A mixer is available in which carrier component cos omega ct is mixed with it and passed through an LP. Okay. So what will be the output? The output is signal output is y of t we have considered, and noise output is n naught of t we have considered. Now this particular part is called as demodulator. Demodulator. Which type of demodulator it is? The demodulator is a synchronous detection. So here I will write using synchronous detection. Okay. This is synchronous detection. Then this whole part I can say it is a receiver. These all things we have discussed in the previous class. Just to analyze the noise calculation model, I am using all these things. Step by step we will see what is the input signal to the demodulator, what is the output to the demodulator, what is the input signal power available at the demodulator, what is the output signal power available at the demodulator. Okay. Now, for this I need to analyze with respect to the spectrum. Okay. So, SF of F plus NF of F. Nice. Now let us consider we are receiving the upper side. Okay. Now USB signal. We have two components. One is USB and one is LSB. So this USB is FC to FC plus B. Let us consider, and this LSB is FC minus B to FC. Let us consider like this. Okay. Now if I am receiving the upper segment, I am receiving the upper segment. So let us consider this is the upper segment. 1 minute. So similarly for the reflection part also I am representing this is the upper segment. Now when I am receiving the upper segment, it will pass through a band pass filter. Okay? It will pass through a band pass filter whose bandwidth is B, because we need to extract the modulating signal, and the modulating signal depends upon the bandwidth B. So here I will say it is FC plus B. Here it is minus FC, it is minus FC minus B. So what is the bandwidth for this upper segment SSB-SC signal? Bandwidth is B. Done. Now here what happens? Here the noise is also added, because we are adding the noise before it is entering to the receiver end, because this noise is available in the channel in which my signal is going to be delivered. Now due to the presence of noise, it will affect my upper segment signal, and I need to identify what is the amplitude. It depends upon what? It depends upon eta naught by 2 that we have seen in our previous diagrams. With respect to DSP-SC signal, with respect to AM signal. Here, suppressing the carrier component, only sideband is available. So I am projecting only these sideband, upper sideband, and that too addition of noise. What sort of noise? It is a white noise or additive white Gaussian noise, whose power spectral density is eta naught by 2. So this particular signal we are going to pass through a band pass filter. And the band pass filter is having a certain band limited to B in order to extract the information. And output of the band pass filter will enter to this synchronous detection, where detection method will be there, and you need to determine what is Y of t and what is N of t. Okay? So we will proceed one by one, step by step. So first, what is the input signal I get? Input to demodulator. Okay. So input to demodulator is after passing through this band pass filter, our S of t will become S of f, because this is the band which is going to pass through the demodulator. Okay. So input to the demodulator is SF of t. Now as per the figure, it shows that we are considering upper sideband. So when we are considering upper sideband, we need to expand, or we need to represent the equation as m of t cos omega ct. Now if it is a plus, upper sideband, if it is plus, if you expand it, you will get a negative component. That is m cap of t sin omega ct. Now this is the expression for SSB-SC signal for upper sideband. So here I will write for upper sideband SSB-SC signal. Done. So this will be my input signal. Next, input noise power is how much? So here it is signal. Input signal to the demodulator, that is SF of t. Similarly, the noise component N of t we have to represent as NF of t, because noise is also going to pass through this band pass filter, and we have written this NF of t with the help of certain sideband representation in the previous class as NC of t in phase component minus the quadrature phase component of N of t. So this is sin omega c. So this will be my input to the demodulator. Input to the demodulator is first signal, which is the received signal, that is called as our SSB-SC signal, which is passed through band pass filter. So this will be my input signal. Okay. What will be the noise component? Noise is also going to pass through this band pass filter, and we are getting NF of t, that is NC of t cos omega c minus NS of t sin omega c. Now I need to calculate the power. Then only I can identify what is the input signal to noise ratio. So power calculation at input. Power calculation at input. Input of what? Input of the demodulator. Because I need to calculate SNR at this point, SNR at this point. Okay. So first, the output input signal power. Input signal power. So input signal power, you can see it is AC square whole into m square of t whole bar divided by 2 plus n cap square of t whole bar divided by 2. Now since these magnitudes are equal, phase is different but magnitude is same. So here we are considering the magnitude. So m square of t and n cap square of t both are same. So it is m square of t we will get, and the resultant is AC square m square of t whole bar. So this will be my input signal power, that is called SI, S suffix I. Similarly, input noise power. Okay, input noise power. Now let us consider this is PR as a notation. Okay. Now input noise power, as you can see, if I will determine input noise power, here I will get NC square of t whole bar divided by 2 plus NS square of t whole bar divided by 2. If you add this, you will get NF square of t, which is the magnitude of this, and whose total power is eta into B. Now why it is eta into B? Since the band is B, for SSB-SC signal, your total power will be, noise power will be eta into B. But in DSB-SC what happens? DSB-SC is twice eta into B. That is the difference. Okay. So input noise power is this. Then I will write what is the signal to noise ratio at the input. Okay. So signal power is how much? PR. Noise power is how much? Eta into B. Done. So this is my input signal to noise ratio. Now the thing is, if this value is greater than this, then the original signal can be recovered. That means the strength of input signal power is more with respect to the noise, then only the extraction of modulating signal is possible. The quality of the signal is not deteriorated. We can extract the information. Okay. But if the noise component is increased with respect to the signal power, then it is not possible to extract the modulating signal. Only the effect of noise can be known. Effect of noise is so much high that it will deteriorate your received signal and the original signal cannot be recovered. Okay. So this is for input side. Now we need to calculate for the output side. Okay. Now let's see. So I will erase this one. So at the output of the modulator, output of the modulator. Now for output of demodulator, I need to calculate signal power, I need to calculate noise power, I need to calculate output SNR. So first I will identify with respect to signal. Okay, the signal is y of t. Now what is y of t? Y of t is SF of t cos omega ct passed through the low pass filter. You can see SF of t multiplied with cos omega ct passed through a low pass filter, that is y of t. So this is my particular value. Now what is SF of t? SF of t is AC m of t cos omega ct and the 90-degree phase shift component of m of t and carrier component. So when I will multiply this cos term to that particular value, this component will become m of t cos square omega ct and it will become as a second harmonic component. So output of this I will directly write as AC m of t divided by 2. Done. So what is the power available? So I will calculate power also. So that is output signal power is AC square m square of t whole bar divided by 4. So this is my output signal power. Okay, AC square m square of t whole bar divided by 4. Done. So this is with respect to signal. Now we will calculate with respect to noise. So what is my noise output? Noise output is N naught of t. What is its value? Nf of t cos omega ct passed through the low pass filter LP. Now the same thing, what is Nf of t? Nf of t is Nc of t cos omega ct minus Ns of t sin omega ct. You multiply cos omega ct to this, you will get cos square omega ct and it will become as a second harmonic component. So cos square will become 1 plus cos 2 omega ct divided by 2. Suppressing the higher component, we will get Nc of t whole divided by 2. Done. Now what is the power available in this? Again we will calculate. So power available in this is N naught, which is Nc square of t whole bar divided by 4. Now the power available in Nc square is same as Ns square of t whole divided by 4, or you can say it is Nf square whole divided by 4, because the same power is available for in phase component, out of phase component, and this Nf square of t. Okay. So now what I will do, I need to divide this signal power and noise power. Then so signal power and noise power, if I will substitute S naught divided by N naught. So S naught is AC square m square of t whole bar. This 4 and this 4 will be cancelled out, divided by Nf square whole bar. Now what is this? This is nothing but your input SNR. So here input SNR. Now the figure of merit is nothing but output SNR divided by input SNR. Take this component to left hand side, it will become a denominator, and the right hand side you will get 1. So remember this, in SSB-SC system your figure of merit will become 1. In DSB-SC system your figure of merit will become 2 with a scale factor 2. That also we have seen. And if it is a AM system, then with respect to modulation index we have represented MS square divided by 2 plus MS square, that is your figure of merit, depend upon the input signal to noise ratio as well as output signal to noise ratio. So this is the basic representation of SSB-SC system. First you need to go through the input of a demodulator, identify the signal, identify the noise, measure the power content in the input signal and the input noise. Then you go for detection of your output signal, that is y of t, or the output of demodulator, and then you can determine output of the noise, that is called output of demodulator. Substitute these values. How we can substitute? Output of a demodulator, S of f multiplied with cos omega ct, okay, followed by LPF, get the resultant value, extract it, suppress the higher frequency component because low pass filter is there. It will monitor only the modulating signal. We will get AC m of t by 2. Take the power component. It is AC square m square of t whole bar divided by 4. You will get similarly for noise component, NF of t multiplied with cos omega ct followed by n. Low pass filter output will be what? Suppressing the harmonic component, extracting the lower component. So lower component is what? NC of t divided by 2. The power content in NC of t will be same as NS of t, same as NF of square of t. Substitute this value, output signal to noise ratio. You will get AC square m square of t whole bar divided by NF. And now this is the thing what we have determined here. The same thing. It is also AC square m square of t. Here also it is NF square of t. The resultant is what? Signal to noise ratio of input. Take this component to left hand side, means denominator it will come. So that is called figure of merit. Output SNR by input SNR is equals to 1. So for SSB-SC system, your SNR will be 1. If it is a DSB-SC system, the SNR will be 2. Okay. So now we will discuss the effect of noise on AM system, or you can say it is double sideband plus carrier system. DSP plus carrier is called as AM system, and the detection will be done with the help of envelope detector. Till now we have discussed with respect to synchronous detection. Now we will discuss with respect to the envelope detection. Now for that also we need to represent the noise calculation model. So first, the received signal, this is a received modulated signal. Received modulated signal added with noise when it is traveling in a particular channel. Let us represent this one as S of t. When it is reaches to the receiver, first it will enter through a band pass filter, which will bring back the higher frequency component to the lower frequency component. The working principle of band pass filter. Next, in synchronous detection, we have used a multiplier in which carrier component is provided and followed by a low pass filter. So the whole system is called as synchronous detection. But the thing is, now we have to use the envelope detection. It is called envelope detection. And as we know, in envelope detector, the signals are added up. Only the magnitude part we are considering. From that magnitude part, we are extracting the modulating signal. Done? So this is the basic representation. So here I will say this is called the demodulator. Okay, and the whole system, including the band pass filter, I will say this is called as our receiver. So here we will determine y of t and n naught of t. Since S of t and n of t is entering, here we will provide S of t and n of t added value to the envelope detector. Okay. So step by step we will see how we can analyze all these things. So let us consider the modulated signal is a AM signal. So S suffix AM of t. So what is its general representation? General representation is AC 1 plus Ka M of t cos omega c. So this will be my received modulated signal. In this, M of t is a message signal with bandwidth of B. Let us consider the bandwidth of modulating signal is B. So this is my AM signal. Next, what is the noise component? So noise component, as we have written, NC of t cos omega ct minus ns of t sin omega c. So this is my signal, this is my noise component. Done. Now these two components are entering to the band pass filter before it enters to the demodulator. So I will write input to demodulator. Which type of demodulator it is? It is an envelope detector. Done. Now SF of t I can write AC 1 plus Ka M of t cos omega c. Now what is Ka? Ka is 1 by AC. इंटरनेट लैपटॉप तो बंद है सर. अच्छा okay. So K is equals to 1 by AC. So this is called as our amplitude sensitivity. Okay. So this is called amplitude sensitivity. Now next, what is our noise? Noise is also same. NF enters to a N of D enters to a band pass filter. We will get NF is equals to NC of t cos omega ct minus NS of t sin omega ct. Done. So depend upon these two, what will be our input to the envelope detector? Input to the envelope detector is F of t SF of t plus NF of t. Additive value. This will be our main point of attraction, because in envelope detector we need to add the component. Okay. So here S of AC 1 plus Ka M of t cos omega ct plus NF of t, substitute the value, NC of t cos omega ct minus NS of t sin omega ct. Done. Now take the cos omega ct component as common. So I will get AC 1 plus Ka M of t plus NC of t whole into cos omega ct minus ns of t sin omega ct. Done. Now this is my f of t. This will be my input to the envelope. Now the envelope monitors only the magnitude. Now let us consider this f of t magnitude I can write as mod of r of t of this component. So what is your R of t? R of t is root over of AC 1 plus Ka m of t plus Nc of t whole square plus Ns square of t. So this is your magnitude. Done. Now when you are determining this magnitude, the two cases will arise. First, the amplitude of this signal is greater with respect to noise. That is your first case. Second, if the amplitude of this received signal is less with respect to the amplitude of this noise, then what will happen? Now for those two cases, we need to analyze what is our R of t. And from R of t, we can extract our modulating signal, as well as signal to noise ratio can also be determined. Okay, so again we will identify these relations as R of t we have found out. So this f of t is represented with respect to R of t. Now what is this R of t? Here we can say output of envelope detector is R of t. That is equals to root over of AC 1 plus Ka m of t plus Nc of t whole square plus Ns square of t. And what is your phi? Phi of t is equals to tan inverse of this component divided by this component. So here I will write Ns of t divided by AC 1 plus Ka m of t plus Nc of t. So this will be my phase and this will be my magnitude. But the envelope detector focuses on the magnitude of a particular signal. Now what is the envelope of this particular signal? The envelope is nothing but R of t. Here you can see this is your envelope and this is your phase. So envelope is nothing but it is a magnitude available in our additive signal provided to the envelope detector. Okay. So R of t is this much, phi of t is this much. Then next we have to identify for the cases what I have told. For case 1, for AC 1 plus Ka m of t is very greater than Nc of t as well as to Ns of t. This is the first case because the amplitude we need to compare, we need to extract, we need to identify the SNR value, we need to identify the figure of merit, then only we can justify whether this system is feasible or not. Okay. Similarly, case 2 for AC 1 plus Ka m of t is less than Nc of t or Ns of t. These are the two cases will arise. This case will justify whether the extraction of modulating signal is feasible with respect to the envelope detector or not. If this component is high, then what will happen? And if the noise component is high, then what will happen? We will see all those. Okay. So first case we will analyze, then we will go for the second case. So first case is case 1, in which the amplitude available in the modulated signal is very greater than the noise component, Nc of t and Ns of t. Done. Now in this you can see If this component is very high, you can neglect this ns square of t. Then if this ns square of t is neglected, then what will be our extracted part? My r of t will become AC 1 plus Ka m of t plus nc of t whole square plus ns square of t. Now since this component is greater with respect to this, you can neglect this component. It is a minimum value. So what I will get as r of t is equals to AC 1 plus Ka m of t plus nc of t. This square will remove out. Then again, this component is again greater than nc of t. You can suppress it. So that means again I can write AC 1 plus Ka m of t. Done. After minimizing the effect of this noise. Next, you need to suppress the DC component, because here in envelope detection or any sort of detection, your DC component must be suppressed. So if you are suppressing your DC component, you will get AC Ka m of t. Done. Now here you can see that AC is multiplied with 1, that will become as a DC component, but AC multiplied with Ka and m of t is a modulating signal. So that means what it indicates? It indicates that if you are proceeding with respect to case 1, if the amplitude of the modulated signal is greater than the noise component, then you can extract your modulating signal. Okay, is it possible? Yes, it is possible. So K is what? K is nothing but 1 by AC. AC will be cancelled out, only modulating signal is available. So that means we can easily extract the modulating signal. And this is quite similar to your DSP AM system. AM system synchronous detection, but in synchronous detection what happens? Here we are getting half. So half is the scale factor when we are using the synchronous detection method, but when we are doing with respect to envelope detection, here it is 1. So that means excluding that scale factor, your signal to noise ratio for the envelope detection using the case if the amplitude of the modulated signal is greater than this is same. So here I will write input SNR of envelope detection is same as input SNR of synchronous detection SB. Similarly, the output SNR of envelope detection is same as signal to noise ratio of output of synchronous detection. Because the scale factor matters. Here the scale factor is 1. So if you divide those two signal to noise ratio, resultant will be same. Similarly, the output signal to noise ratio for a synchronous detection is same as for envelope detection. It is only for the case if the magnitude of the modulated signal is greater than with respect to the noise. So then we can conclude that our figure of merit for an AM signal using DSB-SC plus C or using this envelope detection, your figure of merit is same for your FOM for synchronous detection is equals to the figure of merit of envelope detection for AM system. Only for the case when? Only for the case when your amplitude of a modulated signal is greater than the presence of noise. Then these are my conclusion. Now next case, if I will say, if my amplitude of a modulated signal is less with respect to this noise component, then what will happen? Okay. there are two cases are there in envelope detection. Remember this because the questions are coming with respect to envelope detection also. So you have to identify the difference. First, if the amplitude of modulated signal is greater than the noise component, the whole detection process up to you go for up to this, and in conclusion you mention that in synchronous detection it varies with respect to a scale factor half, which is managed with respect to the figure of merit. So your figure of merit with respect to synchronous detection and figure of merit with respect to envelope detection of AM both are same. Okay, it will change when this case will arise. If the modulated signal amplitude is less with respect to your noise component, then what are the changes will come into picture? In that case, your figure of merit won't help you to same as per your synchronous detection. It will be different. And we cannot measure the presence of signal. We cannot measure the presence of output signal. It is only the noise. Remember this, when we are dealing with envelope detection, first we are adding, then we are processing it. But in synchronous detection, individually we are processing it, then we are identifying the signal to noise ratio and each and everything. Okay. Here in the second case, it is called as a multiplicative noise. It will come. I will justify it. Here it is this much, or it is called additive. We are suppressing the effect of noise. But when you consider for the second case in which the amplitude of modulated signal is less with respect to your noise component, then the multiplicative noise will come into picture. And when the multiplicative noise comes into picture means we are unable to extract the modulating signal. So there is no point of calculation for input SNR or output SNR or figure of merit, because at the end only noise will be there, no presence of input signal. Okay, so that also we will justify. So case 2, we will discuss now case 2. So case 2 states that if the amplitude of modulated signal, received modulated signal is very less with respect to noise component, what will happen? Let's see. So my R of t means this equation. What will happen to my this equation? So R of t is equals to AC 1 plus KA M of t plus NC of t whole square plus NS square of t. Square these two terms. How much we will get? Let's see. So first term is AC 1 plus K M of t whole square. Done. This component is squared plus twice AC NC of t 1 plus K M of t plus NC square of t plus ns square of t. It will be within this root, nc square of t plus ns square of t. Done. Now, as we have considered, the amplitude of the modulated signal is very less with respect to your noise component. So what we can do, this value will become again small, because if it is 0.2, let us consider this whole value is 0.2. If you take a square of the 0.2, you will get 0.04, which is less than 0.2. You can neglect it. So I can write R of t magnitude root over of nc square of t plus ns square of t plus twice ac nc of t 1 plus K A M of t. Why we are not neglecting this 1 plus k into? Because it is multiplied with NC of t. Because NC of t is a maximum value. So if maximum is multiplied with minimum value, again it is a maximum component. So we have to consider this. Now let us consider these two components as Vn square of t. Let us consider this whole component. So what I will write? Vn square of t plus twice AC NC of t whole into 1 plus Ka m of t. Done. Now what I will do? What is my Vn square of t? Vn square of t is Nc square plus Ns square of t. This is a factor. Okay. Now take this Vn square outside. So it will become Vn of t. So here we will get 1 plus twice of AC Nc of t divided by Vn of t, Vn square of t whole into 1 plus Ka into m of t. So this is multiplied with this particular factor. Okay. Now, with the help of the binomial expansion, we had a relation. Suppose 1 plus alpha, that means 1 plus alpha to the power half. If you expand this with the help of binomial function, you will get 1 by 2 alpha dot dot dot. Higher components are neglected. Same thing I am using for R of t is equals to Vn of t whole into 1 plus that root over will divide the two component. We will get AC Nc of t Vn square of t 1 plus Ka m of t. Done. Now if you multiply this Vn of t, Vn of t, you will get AC Nc of t Vn of t 1 plus Ka m of t. Now this is your R of t, means output of a angular detector for a case when your amplitude of modulated signal is less with respect to the amplitude available in your noise component. Now here you can see Vn is a noise component, done. Vn is also a noise component, Nc is also a noise component. So this noise component is multiplied with your received signal. So here it is called multiplicative noise. So this is called multiplicative noise. Done. So this multiplicative noise will hamper to your modulated signal, and the output will again become as a noise component. So it is what it is noise component, and it is worthless to calculate the signal to noise ratio as well as to calculate the figure of merit, because the signal to noise ratio will become depends upon only the noise. So signal quality deteriorates, noise component increases, and we cannot extract the modulating signal. Now from this, can you extract modulating signal? It is not possible, because the effect of noise is so much high that the values will deteriorate. Now what is the Vn of t? Vn of t is nothing but root over of Nc square by Ns square, which is the component, noise component, which is high. If this value is high, you cannot extract m of t. It is hampered to my signal. So what will be our conclusion? Our conclusion is the signal and noise is not so large. Means the noise component is high, signal value is low, due to which signal to noise ratio will be less than 1. If the signal to noise ratio is less than 1, you cannot extract the modulating signal. So these are the effect of noise with respect to the detection method. We have seen with respect to synchronous detection. Now we have discussed with respect to envelope detection. Always remember this. In envelope detection, in the second case, means if the modulated signal amplitude is less than noise, we will get a multiplicative noise. Multiplicative noise means it is very difficult to extract the modulating signal. Okay, we cannot minimize the effect of noise. The effect of noise is so much high that original signal cannot be recovered. Okay, next class we will discuss about effect of noise on AM as well as PM, that is called angle modulation, and then we will compare the figure of merit with respect to AM and angle modulated signal. Okay, thank you for this session. Thank you all.